So, planes, first of all, this R here has exactly the same meaning in a plane as it does in a line. It represents all of the points that are on the plane. So I've drawn it here, but really you should think of that R as a point I could move anywhere on this plane. And as it happens, I know one of the points, 12, 5, 8. Whenever you draw a plane, always draw a normal vector on it. You normally know the normal vector, or you're going to calculate it. In this case, we know it. We're simply told. Now, when we say normal vector, that means any vector that is perpendicular to the plane. It's not technically true that it needs to be sitting on the plane. It's not a position vector. It doesn't have a position in space. It's just any vector that's pointing in a way that it is perpendicular to this plane. It might be pointing downwards. It doesn't matter as long as it's perpendicular. And we're told it is 5, 1, 2. That means that every single point on the plane, if you dot product it with 5, 1, 2, you always get the same number. And we can work out what that number is by putting in the known coordinate. So I can do that. And so now I have the equation of the plane. I can put this back to R, and that is the equation of the plane. Every single point on this plane obeys this little formula here. So it's incredibly easy. Also, if I replace R with X, Y, Z, I can do that simple dot product and write it out like this here. So these are completely interchangeable. This is called the vector equation of the plane. And this is the Cartesian equation of the plane. You see, it's got that Cartesian feel to it. You're familiar with y equals mx plus c, but you don't often see a z coordinate in a Cartesian equation, partly because the equation of a line in Cartesian is a real pain in the neck. That is on our syllabus. But in the case of planes, they are really nice. So when you write a plane down, typically it's written down like this, because it's obviously much easier to write and just clearer and shorter than writing that. But these are completely interchangeable. The advantage of the vector way of doing it is it's very clear that this 5, 1, 2 is a vector. It's a really important vector. It is the normal to the plane. Okay, let's do a few techniques. We've got the equation of plane here, written in both forms, whichever one you find easier, which is bound to be the Cartesian. So is 1026 on the plane? Well, just plug it in. 5 times 10 plus 20 plus 2 times 6, is that equal to 81? No, it's not. Therefore, this is not on the plane. Intersection of a line and a plane. Here's the equation of the line. Here's the equation of the plane. What is the point of intersection? Well, remember that R represents all of the points on the line. R represents all of the points on the plane. So I'm going to substitute this R into there. So trying to stay agile, I'm thinking to myself, what is the nicest way of doing this? I'm going to choose to write the vector equation of the plane of the line as a coordinate. That's x, y, z. And I'm going to write the vector equation of the plane in Cartesian form. It just seems easier. And I'm going to sub this x value into there. So I've substituted the x component, the y component, and the z component into the plane. And I'm going to find a value for lambda. And then whatever it is, I'm going to plug it into this here. And it will give me a coordinate. Let's say lambda turned out to be 10. Well, then it is 22, 14, 37. What is the angle between this line and this plane? Well, we have a formula for angle between two vectors. So I'm going to find the angle between the line and the normal. So just for my own visualization, I have moved the normal to a more convenient location. Remember that the normal is not a position vector. You should think of it as a very movable vector to whatever's convenient. So I've put it in a really convenient place. It means I can very clearly see that I can find the angle between the line and the normal to get this green arc here. Now, how do you do that? Well, the normal is very clear, 5, 1, 2. What should we use about this line? Now, I hope you're saying, obviously, the direction. So I'm going to use the formula for the angle between two vectors on 2, 1, 3 and 5, 1, 2. That is that green angle there. But remember, the question said, what is the angle between the line and the plane? So I'm going to say 90 minus that. So that's enough for this video. I'll send another video for what to do when there are two planes interacting with each other, and another video for the big topic, which is three planes.